All right. And then I time it so that I make sure I don't get caught. So now the next property, I don't know whether this yeah, it can be seen or what is this just going down. So number 1, 2, 3. So number 3, we were saying that you can always you have that correspondence of the eigenvalues, eigenvectors. Then you have now number 4. Ooh, property number 4 here cannot be seen. But number 4 is just talking about let me see, this screen can move a bit. Can it? Ah, yeah, it can move down. Okay. So here, number 4, which you cannot be seen, you can see this. This is just meaning, if I have my matrix, remember, is this one here. This matrix that is n by n matrix over F, all right? In our case, we were looking at the example for a 2 by 2 matrix. So it means that if you have 2 by 2, then you'll have, either two eigenvalues. We had a 2 by 2 matrix, which gave us two eigenvalues. If it's n by n, we'll get n eigenvalues, and they may be repeated, which is called multiplicity. But anyway, so if I have n eigenvalues, if I add them up, then this is the same as taking the trace of the matrix. Now, example, well, trace means that the sum of the main diagonal elements. So, like now, our matrix was A, and let me see whether I can put this in my ear. So, our matrix is A, which is 5, 2, 2, 5. The trace of matrix A is 5 plus 5. All right? Trace of A is 5 plus 5. The sum of the eigenvalues, what are the eigenvalues of A? They were 3 and 7. So 3 plus 7, the sum of the eigenvalues is the same as the trace of the matrix. That's basically another property. Then property number 5 is, so number 4 is about the sum of the eigenvalues. Number 5 is the product of the eigenvalues. So if you take the product of all eigenvalues, if there were n of them, it would be lambda 1 times lambda 2 all the way to times lambda n. It's the same as the determinant of the matrix in question. In our case, and this is a question that Jessica was asking, so our matrix is A. What's the determinant of this matrix? It is 5 times 5 minus 2 times 2, which is 21. 25 minus 4. Now, what are our eigenvalues? They were 3 and 7. So 3 times 7 is 21. So it turns out that this is this correspondence. Then now, more or less, I take a break from the properties. I just add a twist here. Hopefully, you can see again. Is the screen too small, or you can more or less read as I read for you anyway? Here now, I say now we add a twist to this. Now, the twist is to like bring in some factor here. So determine the maximum and minimum values of the quadratic form. Okay, fine. I don't worry about what a quadratic form now. So I don't know, in linear programming or optimization, there's this issue of, you optimize, maximize, profits, minimize costs, things like that, okay? So in this case, we talk about optimize. So you are given an equation, which is this equation, which I'm calling a quadratic form, and you're supposed to find the maximum and minimum values of this subject to some constraint. The constraint is x squared plus y squared equals 1. Now, this I take a pause from the twist and then I said, I give you some definition for this. So what is a quadratic form? A quadratic form is basically degree 2. We can say equations that you can, here I have equations in 2 variables, x and y. And you can see the degrees of the equation are, this is x is squared, y is squared, and then this is x times y. So it's x raised to power 1, y raised to power 1. So this is a quadratic form. And all such representation. If you had degree 3, then I'll be talking about x squared. They may be the coefficient, okay, the constants before the variable. Let me just take a twist here, a shift and then go to like a 3D. Here we have. So here I have, don't worry about the quadratic surface, etc. Think about this equation here. This equation here, look at it. X, the variable x is raised to power 2. The variable y is raised to power 2. The variable z is raised to power 2. Then you have x and y. This is 1 and 1, so it's 2. Then this is x and z, 1, 1. This is 2. Y and z, this is 2 also. Well, okay, this part is not part of the quadratic form. So in this equation, this part is what would form the quadratic form. The ones that are degree 2. All right? Let me see whether we have any other representation. Only that, okay? Now, back to our notes, okay? So, so the quadratic form, all the representation here, I've written Q of x by x. We can represent it as xt, x is a matrix, this is the x a matrix, times the matrix A, the coefficient matrix times the transpose. This means transpose. Transpose of a matrix is the rows become columns, columns become rows. Row 1 becomes column 1, row 2 becomes column 2, and so on. In our case here, this matrix is interesting because this matrix is 5, 2, 2, 5. Row 1 is 5, 2. If you transpose it, it becomes 5, 2. Row 2 is 2, 5. Column 2 is 2, 5. So this matrix, the transpose and the matrix is the same. Such a matrix is called a symmetric matrix. But don't worry for now. So, so in general, you have our matrix, which is n by n. And then we have my variables here. Since we're talking about n, we're talking about n variables. Example, if we have two variables, like our 2 by 2 matrix A, B, C, D, you multiply by the two variables like this. Your x, y, then transpose of this matrix, this row 1 is, column 1 is x, y, which becomes a row, so it's x, y. So if I multiply this matrix times this matrix and this matrix, this is what you end up with. I don't know if you remember how you multiply matrices. In case you have forgotten, I remind you very quickly. So I take A, B, C, D times x, y. I have A times x plus B times y. I have AX plus BY. Then I have C times x, so CX plus DY. These are matrix times this matrix here. Now I'll just be talking about x multiplied by AX plus BY. I'll get AX squared. And then the last one, I had a CX plus DY. Multiplied by y, I have dy squared. And then the B goes with xy, and C goes with yx. So this is a quadratic form. So in other words, this matrix here, this equation of degree 2, I can represent it in this form. Now let me see what page was that one so that I can go direct to that page. It was page 4. This is page 3. Yeah, so let me go and open it. Page 2, page 3. Oh, let's go away there. Now, page 3. Let me see. Oh, I don't know what it shows. Now, this page, anyway, is not giving me what I wanted it to give me. Let me see. I got page 4. One moment, please. Sorry for my disorder here, but it's acceptable. Yeah, so now this is what I'm talking about. So, we see our quadratic form. Let me go to that page 2 here. This is the equation, 5x squared plus 4xy plus 5y squared. This, I can write it in this form. What do? I pull out the coefficients, which are 5, 4, 5. Now, if you pull out the coefficients, I will have what corresponds to x. Now, it's like this equation, I write it in terms of this A corresponds to x and x. So it's ax squared. Then B corresponds to x. The first part is x, and then the second part is y, so bxy. Then C corresponds to y and x, and D corresponds to y and y. So if I go to now, I should get here from this before you go to the other side. I'll have the coefficient for A is 5, so here this should be 5. Coefficient for y squared is 5, so here I have 5, 5. And then B and C, you see this is 4xy is the same as 2xy plus 2xy. So really, this translates into, now where is our page? 4. Oh, here. Page 4 is this. So now our quadratic form, that equation, here it is actually. 5x squared plus 4xy plus 5y squared. This can be written in this form. I write it as xy. This is my x, the variable. Then the transpose of this is xy. And then the middle part, the matrix is 5, 2, 2, 5. Sawa? Up to that point, if I give you anything like this, you can rewrite it in this form. And this is important for what we've just done anyway, the tools we are getting. How? Well, because of what I will say now shortly. But so here now, our Q, our quadratic form, this one here, you represent it as, if I now expand these matrices, if I multiply x transpose, this one, times this matrix times xy, I should get 5 corresponds to xx, so it's 5x squared. And then this guy, y and y, it's like you put x, y here, and you put x, y here. So you have xx, so it's 5xy. Then you have x and y, 2xy, and then here you have 2xy. So it's 2xy plus 2xy is 4xy. And then you have y and y, which corresponds to 5. So it's 5y squared. So this is same as this. Okay? Yes. Now, let me just, again, misbehave by going out and coming back. Now, if I pick, I mean, this was a 2 by 2, I mean, 2 variable case. If I give you a 3 variable case, what do we have? This one here that I've highlighted. Hopefully you can see it. I have 2xy, 2y squared, 2z squared, plus 2xy, plus 2xz, plus 2yz. These are the parts that have degree 2. So how will you write this in that form? Which form am I talking about? This one here, in this form. Well, this is a 3 by 3, so I'll have x, y, z, then x, y, z. Then I pull out the coefficients, all right? Here I'm just talking, but later on probably I will give you this as an example. So I will have the matrix will have 2, 2, 2 corresponding to the main diagonal, and then 2xy. So you can see this is 2xy, 2xy, 2x, 2xz, 2yz. So strictly speaking, what do you expect this matrix here to be? The middle matrix. You expect it to be, let me show you. Tell me before I show you.
I feel like it should have a 2 somewhere. Okay, don't no, maybe just a moment.
You are right, you're right, you're right.
Oh, like
It will have 2 for the
for
2,
the
2, 2.
X, 2, 2,
For
and
these three, for these first three.
uh,
And then the diagonals now they will have,
uh,
let me see where I take you there again. Where?
page 4.
Here. So you see, now we are looking at
Wait,
this compared to this. So when you have 4xy, it means that you split the number you have into 2, you divide it by 2. So now one of the 2's you put here, the other 2 you put there. Right? So for a 3 by 3 case, which is what we're looking at now, you expect to split this one to divide this by 2. So you put 1, 1 somewhere. Then this you divide by 2, and this you divide by 2. So the matrix should be, if you are writing down, you expect the main diagonal to be 2, 2, 2.
2, 2, 2,
And then everything
and
else should be 1, 1, 1, 1.
1, 1, 1.
Yes. So the matrix should be 2, 1, 1, 1, 2, 1, 1, 1, 2. That's what you expect the matrix. That's what should be the matrix, actually. I'm just saying. I mean, in my planning for the lecture, I didn't think I would write it down somewhere, but okay. So that's what you expect for this matrix, okay? Actually, now with that in mind, we've started describing this surface. Let me just say. So this first part, we can write it in the form of this form we are saying here of, the middle matrix here will be 2, 1, 1, 1, 2, 1, 1, 1, 2. And then here you'll have x, y, z. And then here you have x, y, z. Good? That's one of the things I was targeting to talk about, and I have talked about. Okay? Now, so far so good, I hope. Brian and
Yes,
Jessica? Yeah, okay,
yes.
good. Okay, so let's go back to now where we were now, the continuation. So once we have a quadratic form, something comes out here. Now I mentioned here in this page 2, we have, so I'm saying that for a 2 by 2 case, we have xy times this ABCD matrix times xy, which is represented this way when you expand. This middle part matrix, here I'm just saying this it's actually, you can write it as a symmetric matrix. Now, a symmetric matrix is just a matrix that can be, well, symmetric matrix means that the transpose is the same as
Can
a
be.
matrix. In other words, if you take the row 1 is the same as column 1. Row 2 is the same as column 2. I mean, look at this matrix here. Which one? Here. What is row 1? It's 5, 2. What is column 1?
5, 2,
5, 2. What is
5,
row
2,
2? 2, 5. What is
2,
column
5,
2? So this matrix is
2,
symmetric.
5.
And so, if your matrix is symmetric, it is diagonalizable. What does it mean to be diagonalizable? Well, I assume you don't know, so I tell you. Okay? Now, unfortunately, I don't know whether my notes cannot be seen. Can it be seen? No problem. I'll just speak about it. It's supposed to be page, which one now? Page 3, I suppose, the one I didn't capture nicely. Anyway, I was doing this last minute. Next time I'll have a bit better looking kind of slides. But let me just say, so a matrix is said to be diagonalizable. What is missing up here, okay, is, let me just say, is the same as this thing I'm writing, but I just changed the say. A is diagonalizable. Our matrix A is diagonalizable if you can find there exists an invertible matrix. Up here, I'm calling it M, and a diagonal matrix D, such that the matrix A can be written as M times D times M inverse. This is just saying that A is diagonalizable. All right? Definition. Now,
A is
diagonalizable.
if
If you can
if
find
this exists an
in
invertible
matrix
matrix.
M.
Uh,
So invertible means that M inverse exists. This I'm writing like this. M inverse means that it's the inverse of M.
oh,
Now, inverse of M means that M times M inverse is the identity matrix.
mm,
Sawa sawa?
yes,
Okay. And now we can take one more step further, but let me just say example. We have our matrix A, which is 5, 2, 2, 5. All right. We can
yes.
find an invertible matrix M and a diagonal matrix D so that A equals M times D M inverse. Now, how do you find this matrix, this invertible matrix M? And how do you find the diagonal matrix D? Well, all you have to do is just find the eigenvalues. You remember the eigenvalues for this matrix? There are 3 and 7.
3 and 7.
So you place them in the main diagonal, 3 and 7. In the other entries, you put them as zeros. That gives you the
Oh,
diagonal matrix. Nice? Very
oh,
nice. Then now the matrix, the invertible matrix turns out to be, you remember what we found as our vectors? Let me take you back and show you it's
the
page 1.
eigenvectors now for each.
Yes, they were
For each.
minus 1, 1, and 1, 1.
Minus 1, 1, and 1, 1.
So you write that as a matrix. If you do,
Oh,
you have this matrix. So you have found your invertible matrix. We are sure it's invertible because we are sure these are the eigenvectors of 3 and 7. So the eigenvectors of 3, you remember, was minus 1, 1. The eigenvector of 7 is 1, 1. Just to mention, okay, if you wrote your diagonal matrix as 7, 3, which is still okay, then this should
oh,
be 1, 1, then minus 1, 1. You interchange so that 3
oh,
equals.
oh.
Yes, yes. So,
And why is it that?
eh,
Why is it that you see that the invertible matrix,
yes.
why have you not symbolized it as M minus 1?
Okay, I have written M, so I can find, now you can find M inverse, by the way. Once you can find so the A is diagonalizable if you can find this M and this D, so you write A in this form. Then now you're asking, why haven't I written M inverse here? I think that's the question you want to ask, right?
Oh, so you, okay.
But I didn't
Yes.
write it because you can find the inverse of the matrix if you want. For now, I am not interested, okay? For the
Oh,
reasons I'll tell you shortly, okay?
okay.
And where I'm taking you, okay?
Mm.
So, like, I want to take shortcuts instead of going the usual way. In other words, given any matrix, you can always find, I mean, if the matrix is, there's a way you can, some matrices, you can find their inverses. So in our case here, the definition is that the one I wanted you to capture is that a matrix is diagonalizable if you can find M and D, M that is invertible so that you write A as M times D times M inverse. Full stop. For now, that's all I wanted to capture for you. All right. Then here,
Yes.
now I say something else. Now, that's a definition here, which is a kind of hidden. The second part of the definition is, now we can actually take this a step further. If you can talk about diagonalizability of a matrix, then you can have even an extra description of A's. Now, this is orthogonally diagonalizable. Okay? Orthogonally diagonalizable is very similar to diagonalizable. How? In that A is orthogonally diagonalizable if there exists an invertible matrix. Now we were using M, now we are using P, and a diagonal matrix D, such that Instead of writing A as MD inverse, I write A as
P
PDPT.
T.
Now, PT is transpose of this matrix, okay? And one step
Yes.
further here is now the good thing about this is actually it turns out that the transpose of this matrix is actually the inverse of this matrix. So PT, transpose of P, is the inverse of P on one condition. I mean, here there's some condition that you put. The condition is that this, really P is a variation of M. Remember we found our M. Our M are the eigenvectors of our eigenvalues, right?
Yes.
So what do? To find P, all I do is that I convert my eigenvectors into, well, two things. One, they must be the dot product, okay? Dot product means that if I multiply the corresponding x value of this vector 1 times the corresponding vector 2, all right, plus the y value times the y value, I should get 0. So look at this. Minus 1 times 1 is minus 1. Plus 1 times 1 is minus 1 plus 1 is 0. So this is what I've written here. V1 dot V2 is 0. You know what that means? That the two vectors are orthogonal. This is orthogonal, okay? Orthogonality just means that the dot product of the two vectors is 0. Dot product means that I take, this is xy, xy. So x times x plus y times y. I add them up. This is what I'm getting. Are we together?
So sorry. So you've just you've split. You've it's like you've okay. You've multiplied it just by itself, like the minus one. You
Actually,
are
look
doing
at this. Look at this. This is vector 1, okay?
uh
And this is vector 2. So if I take
yes.
dot product, it means I take minus 1 times 1 plus this 1 times this 1. So I can
Oh,
get 0.
oh, okay.
And if that is the case, then I can say these two vectors, this just means
Alright.
the two vectors are orthogonal, this term here. The two vectors are orthogonal, all right? And one more thing here I put in bracket, which I don't know that you can see. Here, this is the vectors R of A are unit. Now, you know what it means, unit vector? They are of length 1. You know how you find the length of a vector? The length of this vector, let's say this one here, 1, 1. You just take, this is x value, y value. So it's x, which is 1 squared plus 1 squared. It gives you 2. The square root of 2 is just the square root of 2. So that means now V2, the length of V2 is the square root of 2. So how do I make V2 length 1? I divide by the square root of 2. V1, the length of V1 is minus 1 squared plus 1 squared. It gives me root 2. So the length of this vector or the size of this vector is the square root of 2. How do I make it unit vector? I divide by the square root of 2. So really, what I'm doing is I'm modifying my M to become P. You can see M and P, what's the difference? M is actually P, only that P is, this I divide by 1 over root 2. Why? Because the length of these two vectors is the square root of 2. Is that coming out more or less okay?
Yes, more or less.
Okay. Now, let me just say why I was taking you here. You remember you asked about M inverse here, eh? Now here, we are good because for orthogonal diagonalizability, once you find P, then you have found P transpose, because what is P transpose? P is this matrix, 1 over root 2 minus 1, 1, 1, 1. What's the transpose of this matrix? The row 1 is minus 1, 1. So it becomes column 1, which is minus 1, 1. Well, do I need to say it? It's the same thing, right?
Yes.
Because the transpose
My
of this matrix is just minus 1, 1. It's the same matrix. So P transpose, it turns out to be, I mean, the same matrix anyway, in this particular case. Number one. Number two, I now can tell you for free. Once we have this, this is okay. I mean, these vectors are of unit length and they are orthogonal. Then this P matrix of ours is transpose. It turns out to be the same matrix. If you take PT, is actually the inverse of the matrix P. Are we together?
yes.
Now I want to
For
give you a quick exercise. Just a short exercise here for us to do. Here, I
okay.
wrote for you, check P transpose times P should give us I. the identity matrix. So take a piece of paper and now you take, what is your P transpose? It's this matrix, okay? So you write down 1 over root 2 times this minus 1, 1, 1, 1 times P times this matrix. So these two matrices, if you multiply, what do you get? You will have 1 over root 2 times 1 over root 2. What is 1 over root 2 times 1 over root 2? Is 1 over 2. Sawa? Then now you multiply this matrix times this matrix. What do you get? We are doing the exercise together. So you can see it's minus 1 times minus 1. It gives you 1 plus 1 times 1. It gives you 2. Are you seeing what I'm seeing or what I'm saying?
Just a bit. Just a bit.
Okay.
Okay, you can continue. Sorry.
All right.
So now you want us to.
So now what I was asking you to check, which we actually were checking, is if you take this P times this PT, we should get the identity matrix, which is 1001. So if you take this 1 over root 2, this matrix times 1 over root 2, this matrix, multiplication of this matrix means 1 over root 2 times 1 over root 2 is a half. So you have a half times this matrix times this matrix. You have minus 1 times minus 1 is 1 plus 1 times 1, it gives you 2.
2.
So you have 2, then the next entry will be this guy here multiplied by this column. Okay, we have been 10 minutes, so good. I think that would be sufficient. So this row times this column is minus 1 times 1 plus 1 times 1. It gives you minus 1 times 1 is minus 1.
Minus 1.
Then plus 1 times 1, it gives you
1.
It gives you 0. This
Wait.
minus 1.
Oh, minus 1 plus
yes,
1. Sorry.
Yes. So it gives you 0. So the first row is 2, 0. Then you go to the next one. This guy here, you multiply by this column, you get 1 times minus 1 plus 1 times 1. That gives you minus 1 plus 1, which is 0. So.
Yes.
And then 1 times 1 plus 1 times 1 is 2. Right?
Yes.
So what do you get? So you have this matrix times this matrix is a half times 2002, which is the identity. So we've verified this. In other words, now the question you're asking me earlier on of finding the inverse of M, I didn't bother because all I have to do is just make sure my vectors are orthogonal and they are unit vectors. Then P, once I have P, I have P transpose. All right? And then the last thing now I say is, so our matrix A is orthogonally diagonalizable. If I can find a matrix P, which is invertible, and I add diagonal matrix D, such that A is P times dpt. So, now particular case, our matrix A, we find, now, how do we diagonalize this guy orthogonally? Well, first thing we find is the eigenvalues, which we did find as 3 and 7.
Yes.
Then we find the eigenvectors, which are minus 1, 1, and then 1, 1.
1, 1.
Then now we modify our M to become P like this. All right? And now we can claim, actually, if you want to check, but I'm not going to bother now, you can check later. Now it turns out that our A is actually P times D times PT. Our P is this, our PT is this. So guess what we have done? We have diagonalized this matrix orthogonally. All right? And now and then now I take you back to where I was. Why was I talking about this? Well, back to our quadratic form. You remember our quadratic form? Q equals 5x squared plus 4xy plus 5y squared. So the question was, in fact, let me take you back to the question. We are more or less looking at our course outline, which is a strange one. Is this question here? Determine the maximum and minimum values of the quadratic form, this one, subject to x squared plus y squared equals 1. In other words, in summary, it's just asking you to optimize. When I could summarize this question by saying, optimize qxy equals 5x squared plus 4xy plus 5y squared, subject to this. So what do I expect you to do? Well, let's go back and say what we are expected to do. So what we expect to do is actually to, let me see whether, we actually do this process of orthogonal diagonalizing our matrix. We pull out our matrix now on page 4 here. Page 4 is like, now we actually rewrite our quadratic form in this form, okay? So we have xtax, and then now we find our matrix P and our matrix D so that A is orthogonal diagonalizable. Sawa sawa? Yes, I'm answering for you. All right? Okay,
Yes.
so the first step is what we have done. We have done the exercise of, if I give you a 2 by 2 matrix, this one, we can always find a diagonal matrix D, and we can always find a matrix P, which is invertible, whose transpose is this, and then we can write A in this form. Sawa sawa?
Yes.
So now this last 5 or 8 minutes we have before we end of this lecture is to say the following. So now from the original quadratic form you have, which is this exercise you're being given here, all right?
5x. Yes.
So we want to transform this thing. So what you will do actually is now you rewrite, you convert now our quadratic form, this one here, which is 5x squared plus 4xy plus 5y squared, you rewrite it into xt, x transpose times a times x, ax. Then this one now I claim this transforms into something new, where here I write it. So our q is xtax can be transformed into this. What happens is that you replace now this part that you have as a, our a you replace with pdt. So you have x transpose times a, but instead of writing a, you write p times d, exactly, and then times x, okay? And then now these are the 1, 2, 3, 4, 5 matrices you are multiplying. X transpose is matrix 1, matrix 2 is P, matrix 3 is D, matrix 4 is
D,
P, and X.
P.
Yes, so these matrices you are multiplying. So I just open the brackets, in other words. Because
Yes.
matrices, you can multiply them. As long as they are compatible, then you can multiply whichever order. We don't care. All right? So in this case, I regroup this into xt, x transpose times p times d times p transpose times x. So I rewrite this now. The last part, I have d in the middle. Then this one is p transpose times x, okay?
Yes.
And now the first part, which is x transpose times p, actually is this matrix. If I take the transpose of this matrix, you know what happens? Take transpose of this guy. Transpose means that now you exchange the order. So you'll have x transpose times p transpose, transpose is p. So this first part becomes the last part taken the transpose. So in other words, we rewrite our original x, t, ax, it becomes a new variable, I'm calling yt, dy. Now, what we have done is to change, we have the old variables, which are xy, they become new variables, and you have this transformation that now the new variable, which I'm calling y, the old variable is x, which is xy. The new variable, which I'm calling y, is here. We have y is ptx. So y is p transpose times xy. Now I can rename them because the old variables was xy, which I was calling x. New variable is, I can call it x dash y dash, which is y. Now, can we do this in the example we had? Yes. So our example, we have, by the way, 4 minutes or less. So let me just hurry up.
Q, X, Y is
So this is what we have. So this
H.
transforms into, you see, our new variable, D, our new variable. So our new variable is x dash y dash. The middle part, we said was, remember the eigenvalues, the diagonal matrix? Yes, x dash. And now if you expand this matrix, you know, how do you multiply out this matrix? You just multiply the diagonal entries with the variable. So you have 3 dash x, or 3x dash squared plus 7y dash squared.
7y squared.
Yeah. So this now has transformed. This looks now like a special form of a circle. It's actually an ellipse. We'll look at an example in the future. But for now, I just want to conclude. Let me conclude the lecture in the next 2 minutes. So to conclude, the maximum. So really, the question you asked to find, this was the question we were solving. So to optimize this, all you want to find is the eigenvalues, eigenvectors. So the biggest eigenvalue will be the maximum value of this equation. And
Okay.
this, and then where is that obtained? The eigenvector corresponding to that guy. So the notes
Okay.
here are telling you that here. So to conclude, the maximum eigenvalue, which is 7, because 7 and
7.
3, which one is bigger? Is 7, right?
7.
And where do we obtain 7? At 1 over root 2, 1, 1. And the minimum eigenvalue is 3, is obtained at 1 over root 2 minus 1, 1. Now let me just look at that page. Hopefully it will allow me. How many minutes do we have? Number 5 here. Hopefully it opens before we close. Okay, so check. We are saying that we obtained 7. Where do we obtain 7? The vector is, the values of x are 1 over root 2, 1, 1.
1 over.
So the value is, the old variable is xy. We modify with this. We have 1 over root 2, 1, 1. You substitute this one into the equation. So you have 5 times x value, which is 1 over root 2, 1, plus 4xy. What is the value of x? Is 1 over root 2, right? What's the value of x? Is 1 over root 2. And then lastly, plus 5 times 1 over root 2, the value of y squared. Does that make sense, the substitution here?
A bit. A bit.
So let me just say this again. Remember our equation is 5x squared plus 4xy plus 5y squared.
Yeah.
What are these values of x and y? The values of x and y are, this x value is 1 over root 2
1 over.
root 2. And the value of y
Okay.
is also 1 over root 2. So you plug in here, the value of x should be 1 over root 2, which you will square, so you get that. The value of y is also 1 over root 2. So
1
here
over.
you